All right, let's prove something that's a little bit more general than the pigeonhole principle. This statement is saying that if you have n elements in your domain and you have m elements in your codomain, and you know that the ratio of n to m has some positive integer k below it. So it's not only that the size of x is bigger than the size of y, but it's bigger by a factor of k. Then you're guaranteed to have some member of the range, y, that has at least k plus 1 distinct elements going to it. So let's prove this and then see how the regular pigeonhole principle follows from it. So let me suppose that I have this entire setup, and I'm going to make an observation and then do a proof by contradiction. Okay, so let me make an observation about the inverse images of individual elements of the codomain. So a little bit of notation to help me do that. If I enumerate the elements of y, then I can make reference to them. So y has m elements, so let me enumerate the elements of y like this. It's got y1, y2, y3, all the way up to ym. Then here's the observation that I want to make. The set X is the set of domain elements, right? So it's going to be the inverse image, it's actually, the union of the individual inverse images of the members of Y. Let me write it out. Okay, so remember this notation. I am not making the claim that f is a one-to-one function. I am simply selecting a subset of the codomain, singleton y1 in this case, and I'm asking for all the domain elements that get mapped to singleton y1. And since X is the domain elements, and every element of the domain gets mapped somewhere, and this is the entire codomain, then X is all of the pre-images of these sets right here. I could write it a little bit more concisely if I use a big union notation. This looks a little bit nicer. Anyway, this says split X up into pieces based on where F maps the individual elements. Okay, and certainly these sets are disjoint because you can't have an element of X getting mapped to Y1 and also getting mapped to Y2. This function is a function, so these are disjoint sets. So sort of the counting principles that we studied in the previous chapter tell us that since this is a disjoint union, pairwise disjoint sets, then the number of elements in X, which is the number n, is equal to the sum of the numbers of elements that we have here, right? And the book would use like an n notation, but I think it's a little bit, well, it takes less ink to use the cardinality notation. Okay, now I want to suppose by way of contradiction that, let's see here, let's look at the last the last sentence of this theorem. Then there is some y such that, well, if I'm going to assume by way of contradiction the negation of this punchline, I'm going to assume for all y in the codomain, y is not in the image of at least k plus 1 distinct elements. In other words, this right here is negated. So for all y in the codomain, the inverse image of singleton y is less than or equal to k. This is my notation for suppose by way of contradiction. Okay, there we go. So suppose that each of these inverse images has at most k elements. That's the negation of the punchline of the theorem. Well, let's see what kind of math that I have then. So on one hand, I have that the cardinality of X is n, right? And on the other hand, I have each of these inverse image sets being bounded by the number k. So I can bound the sum right here that I see. How many terms are in the sum? Well, there's m, 1, 2, all the way up to m, right? So this is less than m times k. So what I have is that n over m is less than or equal to k. But this, of course, contradicts the assumption that's made right here. So this is a contradiction. So there must be some y in y such that there are at least k plus 1 elements that get mapped to y. This is the concise way of saying that. Okay, and how does the original pigeonhole principle follow as a corollary? So this is the original pigeonhole principle. At least let's do part 1. So if cardinality of x is greater than the cardinality of y, then f is not 1-to-1. Well, let's go ahead and let x be n and the cardinality of y be m. And we're supposing here that n is greater than m, right? Well, that means the ratio of n to m is greater than 1, right? Divide both of sides of this inequality by m, then you have the following inequality. So the punchline of the generalized pigeonhole principle tells me that there is some y such that y is in the image of at least 1 plus 1 distinct elements of x. And so f is not 1-to-1. Okay, let me use the generalized pigeonhole principle to answer this question right here. If you have 30 people, must at least 3 of them have been born in the same month. So let's let x be a group of 30 people. And let's let y be the set of months. And let's just make the observation that the cardinality of x is 30 and the cardinality of y is 12. And let's set up a function. So if you put a person in the function, then it tells you what month they were born. Okay, and let's make an observation. The positive integer 2 happens to be strictly less than 30 divided by 12, right? 30 divided by 12 is definitely bigger than 2, because 24 divided by 12 is equal to 2. So this is an integer k, positive integer k, that is less than the number of elements in the domain divided by the number of the elements in the range. So by the theorem, the codomain I should have said, by the theorem above, the generalized pigeonhole principle, there is some element of the codomain, some month, such that, well, the elements of the domain that get mapped to that month is in cardinality strictly greater than 2. So let me kind of write this out into words. The amount of people whose birthday is in month Y is strictly greater than 2. So at least 3 people share the same birthday month. Okay, so this is how to use the generalized pigeonhole principle to make a sort of counting argument like this.